Hi, this video will look at a direct example of how to solve Rankine cycle. So in the last couple of videos, we talked about Rankine cycle concept, and also we made a modification on it. And we realized we have to be flexible depending on if the steam that enters turbine might be superheated, might be saturated. Also, another condition is the water come into the pump could be compressed liquid or saturated liquid. So in that situation, you have to be flexible. Then that would govern how the Rankine cycle look like. So here we have one perfect example to look into it. Whenever I solve any power cycle problem, I like to draw. I like to put the things on the graph. I think it's clear that way. So let's do a quick drawing or recap of what we've done before. So here is our pump, and then after through the pump, we're going to go through the boiler, and then we'll go through this turbine, and then going through the condenser. Then going back to the pump. So that's the entire cycle process. And we'll go ahead and draw our TS diagram. And in order to do that, we're going to put our letters corresponding to it. So this, we start on here, A, and this is going to be B, coming out of the turbine, C, coming out of the condenser, D, and then coming out of pump, E, and we know why there's an extra one, right? E is compressed liquid and A is saturated liquid. So when we're about to draw this onto our TS diagram, first we're going to know this power cycle running at two different pressure, high pressure and low pressure. And this is going to be our high P, and this will be our low P. And let's go ahead and label it. This is the steam enters the turbine at 1.4. That's basically at a higher pressure. That's 1.4 megapascal. And then it enters the pump, which is right here. That's low pressure, and that's 4 kilopascal. So knowing all those conditions, we're going to start to translate our A, B, C, D, E onto this TS diagram. How do we do so? We know A is a saturated liquid. From A to B is a constant pressure, and also it's constant temperature. And then from A to B, now we need to really figure out, is this B at 1.4 mega and 500 degree, is that superheated vapor or is it saturated vapor? So in order to do that, we're going to bring up our steam table. So let's look at steam table for 1.4 mega and 500. So 1.4 mega, which table A5, that's 1400, right? 1400 kilopascal. Let's take a look. The saturated temperature is 195, so we can write it down. T sat at this 1.4 megapascal, the temperature is 195 degrees Celsius. However, our temperature is 500 degrees, way greater than our T-sat. So what does that mean? That means it is superheated vapor. So it's a superheated vapor, and it's going to be somewhere here. That's going to be our B. Then let's go back to this Rankine cycle. From B to C, it's turbine, which is ideal Rankine cycle. That's going to be isentropic process. So it's going to be straight down line here. That's going to be our point C. And from C to D goes through condenser. It's a constant pressure and also constant temperature. And here we need to take a moment to figure out, is this D as saturated liquid or is it compressed liquid? And let's go back to the problem. It says saturated liquid enters the pump. Then that gives us a clue. That's going to be D right at the saturated liquid. Then we're going to go through the pump. Again, it's an isentropic process from low pressure line to the high pressure line, jump up, and constant S, isentropic. Then that's going to be our E, which is compressed liquid. From E to A is going to be the saturated liquid. Okay, so we have this graph that's going to be our Rankine cycle for this particular problem. Now we're going to figure out the first problem, the pump work. So if you need to review what we talked about last time, for each of these 4 components, we have a equation for each one of them. For example, for pump work, that's required work coming. It's right here, right? And also turbine, generator work out. Then for boiler, we require heat coming, and for condenser, it's have heat leaking out. So for pump required work coming, we have a couple of expressions. We said it's going to be mass flow rate, HE minus HD. Another expression is or VD, specific volume, times our, or here, or volume, then it's going to be high pressure, which is PE minus PD. So either of those work. Now here, we have to figure out which one works for us, okay? So if we're going to use this first expression, HE minus HD, okay, so can we figure out HD? If that's our logic, we're going to find HD. What's the enthalpy at point D? D is saturated liquid. So that's going to be HF at this particular pressure line. This pressure line is what? 4 kilopascal. So we're going to go to our table A5 to find out what's going to be at 4 kilopascal, table A5. Let's see. What's going to be our HF? It's 121.39, right? Kilojoule per kilogram. Okay, then we find 1. That's pretty good. Now we need to find HE. E is a compressed liquid. And what condition do we know about E? We know the pressure is 1.4 megapascal. And other than that, we might be able to find the second property. But let's go. Let's see, HE, it's compressed liquid. If it's compressed liquid, we're going to look at table A7. And as you already predicted, at table A7, the lowest pressure they have over here for compressed liquid is 5 megapascal. And here, our pressure here is 1.4. So we cannot really use compressed table to solve this. We have to approximate, right? We're not quite stuck. We can still approximate. How do we approximate? That's one of the things we're talking about. It's going to be using the saturated liquid HF at that particular temperature at E. This point right here, TE. Well, how do we find the temperature at E? We haven't figured that out yet, right? So we do not know this TE. If we don't know that TE, it's going to be hard for us to figure out HE. So here we're kind of in a crossroad. Then I just say, maybe I can look for this alternative way, this way. Can we do it with this? Yeah, let's take a look. Can we figure out the specific volume at D? Yes, we can, because D is saturated liquid. So I'm going to go back to step 1, find VD. We're going to find a VF, specific volume for saturated liquid at 4 kilopascal. So I'm going to go back to the same table, table A5. Table A5, and we're going to look at 4 kilopascal. At 4 kilopascal, and our specific volume VF is this value, is this one right here, 0.001004. Let's just double check. I got the number right. Yep. So that's going to be in unit of meter cube per kilogram. That's our specific volume for D. Then we can go ahead and put into that formula to find out our pump work. So our pump work coming is going to be equal to VD, which is 0.001004 meter cube per kilogram. Then our PE, the highest pressure is 1.4 megapascal. If we were changing that to kilo, it's going to be 1400 kilopascal minus no pressure at D, D is at there's no pressure, so it's 4 kilopascal. So that's going to give us this. All right, now before we put things into calculators, think about the unit. Kilopascal times meter cube. So kilopascal times meter square, that's pressure times area. That's going to give us the force, so it's kilojoule. Then, so kilopascal times meter cube, I'm sorry, kilogram. That's a force kilogram. Then times meter cube, it's basically force times distance. That's energy, so give us kilojoule. So the whole thing going to give us a unit of kilojoule per kilogram. Okay, now the rest is calculation, and I'm going to put it in there. 0.001004 times 1396, and I have an answer for that as 1.4158. That's going to be the work required for the pump. And notice the unit is kilojoule per kilogram, so that's basically the work per unit mass. That's what they're asking. So we have that down. Now the next problem we want to figure out is what is the turbine work. Okay, so turbine work is going to have a different formula. So for turbine is generate work out. That's going to be mass flow rate of initial enthalpy, which is HB, right? B minus C. HB minus HC. Now let's think about it. HB is enthalpy at B. We already know B is at a superheated vapor state. Then we can go to the corresponding table to find what's the enthalpy at that condition. So HB, and it's at 1.4 megapascal, and it's at 500 degrees Celsius. So I'm gonna take out the table out. We move to superheated, and it's 1.4 megapascal. Let's go to the corresponding milli table. I believe it's going to be right, this one. 1.4 megapascal, and the temperature is 500, if I remember. Yep, so it's 1.4 and 500. So that will give us the corresponding enthalpy. Will be right, this one. 3474.8. 3474.8. So that's going to be the enthalpy, so it's in kilojoule per kilogram. That's HB. Now we need to figure out HC. At C, we know one condition. We know the pressure. But what would be the second property we need to know in order to find HC? So don't forget, this is the ideal Rankine cycle. You probably already figured out it's isentropic process. So in other words, my SB is gonna be equal to SC. The entropy stay the same. So I'm gonna go back to find out my SB. It added the same superheated table. So my SB at 1.4 and 500 degrees Celsius will be this value, 7.6047. 7.6047. That's gonna be our entropy, and that has a unit of kilojoule per kilogram per Kelvin. Okay, so knowing that, we know our SC will share the same value. Now we have two properties now. At point C, we not only know about our entropy, we also know the pressure at point C. That is at no pressure, 4 kilopascal. Now we're going to go back to the pressure table, which is table A5, see how this entropy located in terms of SF and SG at that pressure. So let's go to table A5. Table A5, and we said it's going to be at 4 kilopascal. at 4 kilopascal, and if we look across, and we can look at our SF and SG. Our SF is this value, 0.4224, and SG is 8.4734. And so we know we're going to write down those values. SF is 0.4224, and SG is 8.4734. 8.4734. That's our SF and SG value. So you know our entropy right here, as it's in between those two values, so we know it is a mixture. Not only that, you actually kind of already draw that way in your TS diagram, because C is located in this dome. That's gonna be a mix, right? So in that situation, what do we want to find out, by the way? We want to find out HC. So we need to go find HC. In order to find HC, it's a mix. We have to find a quality X. So X is going to be our jumping board. X is going to be using S minus SF over SFG. And what is our S? Our S is share the same entropy as B, which is this value, 7.6047. And our SF at this pressure, it's 0.4224. And our SFG will be SG minus SF, or you can take out direct from the table, which is 8.051. 8.051. Okay, so here we are going to use our calculator trying to figure out our quality. So 7.6047 minus 0.4224, then divide by 8.051, and we have a value for quality. It is 0.892. That's our quality. So once you find out quality, then we can find our enthalpy H. And using the formula HF plus XHFG, then we can solve it. Remember, this is at 4 kilopascal. So we're going to go back to the 4 kilopascal, finding our enthalpy. So our enthalpy for that is 121.39. And our X is 0.892, and our HFG is going to be this value, 2432.3. So then we can find our corresponding enthalpy at this point C. So put it into calculator, 121.39 plus 0.892 times 2432.3, and I have 2291. Hopefully you do the same. That's going to be kilojoule per kilogram. That's going to be the enthalpy at C. Voila, we're almost finished, right? So going back, our goal is to find out what is the turbine work out, how much work is generated. It's going to be this HB minus HC, and eventually you know what you're trying to calculate is work per kilogram, so it's work out divided by mass flow rate. HB, our HB is this value right here. For superheated, 3474.8 minus HC, this value, 2291. All right, when we go ahead and do that, 3474.8 minus 2291, we have a value. It's 1183.8 kilojoule per kilogram. That tells us how much workout per unit mass for the turbine is. Okay, so far we finished two problems. We finished the pump work and the turbine work. Take a moment to compare those two answers. For the pump work, we have, I believe our pump work is right here. And it's 1.4. And this one, the turbine work, is 1183. Isn't that amazing? The difference between them? That is the reason often the pump work is negligible. Okay, so knowing that, we're going to look at the third one, the backwork ratio. This is a concept we first are going to talking about. The backwork ratio, it's very simple concept. It's basically what's the percentage of the pump work compared to turbine. Since you already know both of them, that will be easy calculation. One is 1.40158. Turbine is 1183.8. So when we go ahead and calculate that, (1.40158) divided by 1183.8. Then we have a value here. It is 1.184 times 10 to negative 3. If we are changing that to percentage, that would be times 100. So that would give us 0.1184 percentage. Okay. So that's backwork ratio. Let's continue. They ask about the amount of heat added at high pressure. The amount of heat added at high pressure is basically how much heat added, change from compressed liquid to saturated liquid, and then saturated liquid to this superheated. So it's this red line all over here. That's going to be the heat required. All those, that's going to be heat required in the boiler. So for that, we can go ahead and solve our number 8. So heat required for that situation, it's going to be our final enthalpy, which is B minus initial E. So it's HB minus HE. Okay. Again, since it's the work kilojoule per kilogram, we just needed to find enthalpy change. Do we have HB and HE? We know HB, right? From previous, it's 3474.8. 3474.8. And however, do we know HE? We don't, because we were stuck here at the step 2 when we were trying to figure out the pump work. And then because we couldn't figure out HE, we used the second alternative way to figure out the pump work using V times pressure difference. Now how do we figure out HE then? Right? So this is actually go around way. I think it's actually creative. How do we do that? Because now you know the pump work. The pump work is 1.40158. That is also, I'm gonna write it down. The pump work, now it's known. That is also equals to the enthalpy change of E minus D, HE minus HD. And this pump work, you calculate using V times pressure difference as 1.40158. That's your pump work. And we also know our HD. D is our saturated liquid. Right here, you figure out HD here. We just didn't use it before. Now it's time to use it. It's 121.39. 121.39. All right, just make sure I got the number right. Okay, so then in that situation, you can use this way to find enthalpy at E. Isn't that something, right? So it's 1.40158 plus 121.39. Then you figure out HE is 122.79, about, right? 158. Then knowing that HE, you can bring it back to this one here, 122.79, 158. Then we can figure out the heat required. So it's 3474.8 for superheated minus 122.79158. That's for the compressed liquid enthalpy. Then we have an answer for that, 3352.00842, and that's gonna have a unit of kilojoule per kilogram. That's help us to answer the amount of heat required. Okay, the very last one, but last but not least, the thermal efficiency for this Rankine cycle. Okay, we're talking about there are a couple of formulas to find this, and we said last time is desired over required. Desired is work net, right? And basically it's your work for the out for the turbine minus required work for the compressor, then divided by the heat required by the boiler. And we have expression for that. Since we already solved in this problem each individual term, we can just use this formula. Work out, that's by the pump, that's by the turbine. And we have a value for that, which is 1183.8. 1183.8. And for the pump required work is very small, is 1.40158. And the heat required, we just calculated, it's this value, 3352.00842. I obviously put too many decimals, but now let's go ahead. 1183.8 minus 1.40158. Then we're gonna divide it, 3252. All right, I think that's enough. That equals, so I have thermal efficiency for this Rankine cycle as 36.36%. All right, that wraps up this example for Rankine cycle. Hopefully you have a better understanding how to solve Rankine cycle and for your future FE and PE exam. And so I'll see you next time. Bye.